Now to the next section, radar cross-section prediction. There are two main categories that you can break down the prediction calculation methodologies: exact techniques and approximate techniques. And we're going to take them just in this order. Then, of course, we'll compare the different methodologies with their strengths and weaknesses. Before we delve into these, I'd like to go over for a minute or two with you that this is a very applied, mathematically oriented subject, and this is the second generation of Merrill Skolnick's handbook. In that handbook, Eugene Knott wrote about a 50-page section on radar cross-sections, and he also, in the third edition, wrote another somewhat upgraded 10 years later version of the handbook. And here is his textbook that he's written with two other colleagues called Radar Cross-Sections, and this is 500 pages. And the version in the radar handbook is 45 pages. But in the introduction to Merrill Skolnick's, in the introduction to radar systems written by Merrill Skolnick, which is our text, the details of these radar prediction calculations techniques are not gone over, aren't gone over. But I feel it's important because over the past decade, I haven't felt that there's been enough of a first or second level treatment, just an hour or so's worth on all of this material. So I thought in this particular course that I put together, I'd include a section that would go over the first and second level of these techniques. They're all described in great detail in these books, and in Gene Knott's textbook are hundreds upon hundreds of references to the authors that wrote the papers that this book rests on. And some of them have been really monumental papers. I remember back when I was an undergraduate and I was studying the Rutherford's model of the atom, that it wasn't a solid mass, that it had a nucleus, and there was mostly nothing around an atom. The matter was in the nucleus, and the electrons didn't amount to much of it. Rutherford's experiment found that out, and it was written up in a 1928 philosophical magazine article. So I went over to the MIT library, looked it up, and when you pick up the volume in paper, you can just see a very dark line around the center of it. You open it up, and that's Rutherford's article. There have been a lot of articles of Rutherford's, but there are seminal articles that I will refer to in these different techniques, methods that you can look up from looking at references in either Eugene Knott's version of the chapter in the radar handbook or his book. I know that Eugene Knott has written a couple of survey articles for the IEEE proceedings in the last decade or two, and they all put this material down in smaller, more compact language than the real heavy mathematical complexity. And what I've tried to do is lighten it even further so that I'd emphasize more the physical principles involved in the techniques and their limitations and roughly how they work, rather than get into the weeds and the details for this level. But so that when someone says we use geometrical optics to calculate this, or physical optics with diffraction, you'll have a physical understanding of what that means. And that's the goal of this next section of the talk, which is going to last, probably 40 minutes. Okay, so let's first look at the exact techniques. So there are two of them: the finite difference time domain technique and the method of moments technique. And then later on we'll move on to the approximate techniques. And here's the way I've outlined them. There's a method and the approach, the one-line approach. in the finite difference time domain technique, the so-called FDTD approach, we've solved the differential form of Maxwell's equations for the exact scattered field. And you know, if you just take the magnitude of the scattered field, divide it by the magnitude of the incident field squared, add a 4 pi r squared, and the limit as r goes to infinity, that's the cross section. So that's the way we get that. This is the approach we take for the finite difference time domain method. And now let's take a look at exactly what that is in one view graph, just words. It's an exact method for solving the radar equation, calculating the radar equation. What we do is, as I said earlier, we solve the differential form of Maxwell's equations. And we note that this is going to base its underpinnings on a change in the electric field in time is dependent on a change in the H field across space, and vice versa. A change in the H field in time is dependent on a change in the E field. The differential equations for Maxwell's equations are transformed into difference equations. And we'll get into it in a minute, we'll get into what difference equations are if you haven't studied them. These difference equations are used to sequentially calculate the electric field at one time, and use those electric field calculations to calculate the H field at an incrementally greater time, etc., etc. We bootstrap it with, in between we calculate the E fields as a function of H in time. It's a bootstrapping method, and it marches in time. These time-stepped E and H field calculations avoid the necessity of solving simultaneous equations, and that's the great part. And it's a good approach for structures with varying electric and magnetic properties and for cavities. Okay, let's look at this technique in a simple case that's easiest to visualize. A two-dimensional problem. There's no variance in the y direction. D by dy of all the fields is 0. Okay. And the equations decouple into an H field polarization and E field polarization. And the H field polarization just has an H sub y, an E sub x, and an E sub z. And the E field polarization has an E sub y, and that's in E in the y direction, and H fields in the x and z directions. Now, using that property that we're not going to have any y dependence, a bunch of these equations drop out, and the equations decouple into H field and E field polarizations. And so this is the relationship we're going to focus on. How do we go back and forth? And here is that equation we're going to focus on. And we're going to use the Yee's lattice. And this is there's a classic paper that's referenced in both the handbook and in Knott's book on Yee's paper, if you'd like to look it up, where Yee broke down space into a lattice along the x and the y direction, and here, since we're dealing two-dimensionally, well, the y direction would be going into the paper, into the view graph. Okay? And here we have the solid blue line is EZ, and this vector here is the E field in the x direction. And so if we take an arbitrary coordinate system where x and z are located right here, this equation goes into this discrete form. And you see that what we're doing is, when you put it in this discrete form, what you have, if you look everywhere in, well, these two components are this differential. And these two differences are this part of the H-field polarization equation, and this set of two entities are this differential in the EZ direction, and these are in the EY direction, and this is the HY, this large one. Now, if you look at these equations, you can put the electric field, you can put this expression of the magnetic field on one side and all these others on the other side, and all of the others tell you the sum on the right-hand side of these 5 different terms tell you the H sub y term at a time delta t over 2 greater than t0. So what you've done is you've made an approximation. You've got an approximation as good as small as the delta t is to what hy is as a function of all these other terms at t sub 0. And that's essentially what you do to all the different terms in Maxwell's equations. So it allows you to inch your way forward in time. And at first, calculating an H field at a time greater, and then calculating a Y field at a time greater, and the same thing with calculating the differentials at greater. So we're marching in time. So the fields at these lattice points can be evaluated as time progresses. And what you need to do is to just put in the initial conditions of what the field is to begin with. And you know, since our incident field's a plane wave, we'd put in say a Gaussian lump of plane wave and see how that progresses in time. Now, the problem one has to deal with this kind of a calculation are the boundary conditions and how we handle them. Because if we put a perfectly conducting boundary, then we'll get reflections off the boundary, and that won't be appropriate because free space doesn't have a boundary. And so there are certain absorbing boundary conditions, a first-order absorbing boundary condition at the edge of this absorbing boundary, which is this differential equation, and also at the boundary between a perfect conductor and the absorbing boundary, we can put a second-order absorbing boundary condition. These absorb ABC conditions are used to limit the computational domain. The reflections at the exterior boundary are minimized, and the traditional ABC models fields as outgoing waves to estimate the field quantities outside the domain. And more recent perfectly matched conditions, you see, that model uses a non-physical layer that absorbs waves perfectly. And if you'd like to read more about these techniques, you're welcome to go to NOT, and it will give you 4 or 5 pages on them to look at them. So these are how these FDTD methods are used. You can use them with single frequency calculations where we excite with a sinusoidal incident wave, and that's what we're going to be looking at today. We run the computation until steady state is reached, and we calculate the amplitude and phase of the scattered wave. And you can use them with multiple frequency calculations where we excite again with a Gaussian pulse incident wave, calculate the transient response, then take the Fourier transform of the incident pulse and the transient response, calculate the ratio of these transforms to obtain the RCS at multiple frequencies. Now, to show you the utility of this technique, giving you a very good understanding of what happens when a pulse of plane wave, a Gaussian pulse of a plane wave, monochromatic plane wave, impinges on different metallic surfaces. We have here a number of different cases. I believe in the course of this discussion on finite difference time domain simulations, we're only going to look at a number of these. In this first section, I'm going to talk about case 1 and case 5. And I'm going to show you these simulations, and we'll go through in a couple of steps before I show you a video. In the first case, we have a Gaussian pulse plane wave incident, and the E-field polarization we have. So E sub y is plotted. E sub y, and it's a ½ meter in width is the pulse, and our perfect conductor is 4 meters long. And we're going to look at two things: the reflection of the pulse off of the metallic perfect conductor, and also diffraction around it. So we'll see specular reflection, but also we'll see that some of the energy goes around, so we'll see some diffraction. And this is a time sequence of photographs of that movie I'm going to show you in a moment. And notice positive quantities of the field are in red, white is 0 field, and blue is negative. You see first that the field comes in. Here it's right at the plane wave. What you've really got is the current canceling out the plane wave. And here we have the induced current in the metallic surface has given rise to an electric field with negative sign, as you get when you bounce that polarization off of a metallic conductor. We saw that in propagation when multipath would bounce off the ground. It'd flip the phase to -1. That's that -1 we're seeing. But also notice that around the back of the this conducting plate, we see some red, which means there's diffraction of the incident wave around the back. You can see it here. It doesn't go in too far, and it's weak, but it's there. Now let's go to the movie. Here we see the Gaussian plane wave coming in. Here's the metallic, perfectly conducting metal plate. And here we see it inducing currents, and the induced currents give way to a reflected specular of opposite sign, and you see around the edge some diffraction. Now I'm going to show you just one more time the simulation of the scattering by the strip. Again, this is a conducting plate. There'll be an electromagnetic wave, plane wave, red positive, blue negative amplitude that will come in. And for the tangential electric field to be 0, it has to go to 0, but it induces a current with the opposite, which generates an electric field with the opposite amplitude. And we see some diffraction around the back of the plate. and it moves off. And now let's look at one more example. This example is of a cylinder, and it's a two-dimensional example, but it'll show you the phenomenology of that oscillating of the sphere, of the cross-section of the sphere that I showed you. And that oscillation is caused by the interference of the wave that comes down and hits the front of the sphere, and then what happens is a wave is generated called the creeping wave, which goes all the way around this way and all the way around this way, and they come back and they constructively or destructively interfere with the incident wave. If you're sending a sine wave in, we're sending just a bump in of energy. The time difference is such that you won't see it. But the creeping wave effect you'll be able to see quite readily with this. It's a Gaussian plane wave incident. The H field polarization, HY, is plotted here. This is the HY. Okay. And that's in that direction, in. Okay, and this is 2 meters in size. Now here's what happens. We have the field come in, and we have the field scatter out with the same magnitude, but we also have coming around the back of the field, coming around the back of the wave, this creeping wave, which interferes, which is generated and will come back out with much smaller amplitude in this case. And now let's look at that example. Let's set it in motion. Plane waves coming in. It's scattered back. We see the creeping wave there coming around, going back. It's light, but you can see it, I hope, through your... I can certainly see it on my computer screen. Let's look at that one more time. I'd like to just add that these movies were put together by Bob Shin from MIT Lincoln Laboratory and some friends, and I'm indebted for their use. Here we see the scattered wave come back. And then as the wave comes around, it creeps around the back and comes out. Here we see the creeping wave. And of course, this is at one frequency. Now, this is from a work done by John Reinstein and published and shown just about in every textbook as an example of a creeping wave. Here's the electric field in arbitrary units and distance from a sphere of radius. And these units are 2, 4, 6, 8. And the distance in sphere radii. And here you see the specular return. And then a distance later, the creeping wave return. So we see the creeping wave comes out, and the specular wave comes back and forth. And this is the radius of the sphere is equal to the radar wavelength. So what you can have is that interference effect taking place.